But what exactly does this mean? Let's take a look at building a dam. So when we go to build a dam is a big old piece of wall that's attached, and it's holding water behind it, so there's water behind it. So if we look at the pressure behind there, we've got a little bit of pressure here, greater pressure here, greater pressure here, greater pressure here. It needs to be thicker down here. So actually when we build dams, they go out like this. So they're much thicker down at the bottom than they are at the top in order to hold this pressure. But what about the pressure here compared to the pressure over here? Well, let's draw our ground. You can see that none of this has anything to do with this. There's no horizontal distances in there at all. It's all vertical. So as h gets larger, here's h is getting larger, h is getting larger, h is getting larger, my pressure goes, this pressure here is going up, so I need to push back more. Good way to think about this too is when you're gonna go swimming. So here's the swimming hole where I grew up. Notice it's brown. That's because all swimming holes are brown. Let's take a look at pressure over here at A and the pressure over here at B, because you've got this little cave that's going in, my little yellow fish. There's no yellow fish. But anyway, over here at A and B are at the same depth. However, now let's take a look at, this is over here at A, this is 5.5 meters deep. And then I've got this little cave that's over here, and this height over here is just 3 meters deep. So I've got 2.5 meters of dirt above it. So this is static, it's a pond, it's a hole, so that means there's the acceleration of my water is 0 and the velocity of my water is 0. What's my pressure at A? Oops, wrong side. My pressure at A equals what? So, P2 equals P1 plus rho GH. I want my pressure at 2. That's going to be, so pressure at A is going to equal P1 plus rho. Ooh, that's a horrible looking rho GH. So I have to draw my little square like I did before previously in my beaker here. But notice this H is completely arbitrary. So I'm going to draw my little square like this. So now the top of my square reaches all the way up to the top of the, and my H is 5.5 meters. So I've got P1 pressing here, P2, which is going to be my pressure at 2. That's the same, as long as I'm at that level, it doesn't matter. I have rho GH, and my H is going to be 5.5. But I've made the top of my little square at the top of my pond. What's pushing down on there? Air. So this becomes air pressure plus the rho of the water times G times my H, which is 5.5 meters. Ooh, air pressure. What is air pressure? Well, that's what this handy sheet is for. So if we take a look here, and look real close, where is it, where is it, where is it? There's that. 1 atmospheric pressure, ooh, oh, it's in the way. 1 atmosphere pressure equals 1.0 times 10 to the 5th newtons per square meter, 1.0 times 10 to the 5th, oops, pascals. So, whoa! All right. This turns into, oops, wrong side. 1.0 times 10 to the 5th pascals plus the rho of water. Water, again, by definition, is kilograms per cubic meter. 1,000 times G times 5.5. Do all your math, and this turns into, this is 1, 2, 3, 4. 1, 2, 3, 4 plus 1, 2, 3, 4, 5. And this is now 1.55 times 10 to the 5th pascals. That's the pressure down here at A. What about the pressure at B? All right, so we have 3 meters here. So P2 2 equals P1 plus rho GH. Oh no, I've got two things on top of each other, so P1, I'm going to have to figure out, oh wait, no. It's at the same depth. This water's not moving from one area to the other. So even though it's moved sideways, the pressure at A equals the pressure at B, which is 1.55 times 10 to the 5th pascals. Moving horizontally in the fluid doesn't change the pressure. When we go back to our dam, that's why moving this way doesn't change anything. That's why when you stand at the edge of over here, but all this water's out here, when you stand at the end of the ocean, you don't get crushed because it's only the depth of the water that affects you.